Second order linear differential equations are a lot trickier to solve compared to the first order case. Nevertheless, there are some methods that we used in the first order that we can still use and apply for the second order case. Most notably, the variation of parameters technique. So this is the standard form of a second order linear homogeneous differential equation. I'm going to assume that you already know the general method for solving these types of homogeneous equations. I'm going to briefly write down the prerequisites for this video. So we have the characteristic equation, which is a2 r squared plus a1 r plus a naught is equal to 0. So this is the characteristic equation of our differential equation. And we find the roots of this polynomial, second order polynomial. So r minus r1 times minus r2 is equal to 0. And in this video, I'm going to derive the solution to the homogeneous differential equation in the case where the discriminant of our characteristic equation is 0, which means that the roots are equal. r1 is equal to r2. In the case where you're not familiar with this notion of characteristic equation, I'm going to briefly show you what it means. So we're going to have a trial solution, which is of the form y is equal to e to the r1x, where r1 is a solution, or a root to this second order polynomial, and therefore y prime is equal to r1 e to the r1x, so we differentiate, and similarly y prime is equal to r1 squared e to the r1x. And remember, r1 can be complex when delta is less than 0. So let's see if this trial solution actually works. So I plugged in our trial solution into our differential equation, and so we get this expression, and we can factorize by e to the r1x, which gives us this product. But we already know that r1 is a root of this polynomial, and so this whole expression is equal to 0. And that's why we're interested in this characteristic equation, this second order polynomial, because it gives us information for one of the solutions to our differential equation. So now we know one part of the solution to our differential equation, which is of the form c e to the r1x. And the reason I put a c here is because we want to be a general solution. And so we have 1 degree of freedom, but this is a second order differential equation. So we need 2 degrees of freedom, and therefore 2 constants. So we need to find one more solution. When the discriminant is not equal to 0, we have 2 roots, 2 different roots, 2 distinct roots. So we know that a solution can be of the form c1 e to the r1x plus c2 e to the r2x, where r2 is the second root of our characteristic equation. So here we see that we have 2 constants, which is perfect because we have a second order differential equation. But what if the discriminant is equal to 0, and therefore r1 is equal to r2? Well, we have a problem here because the solution can't be of this form. And let me show you why. So we have y is equal to c1 e to the r1x plus c2 e to the r2x. But since r1 is equal to r2, I have c2 e to the r1x. And we can factorize by e to the r1x, which gives us c1 plus c2, which gives us e to the r1x times c, where c is equal to the sum of these 2 constants. And therefore, we only have 1 degree of freedom, which is not enough in the case of a second order differential equation. Therefore, we need to resort to other methods of finding the second part of the solution to this differential equation. We already have one part because c1 e to the r1x satisfies this differential equation, but we need to do more work in order to find the second part. And this is where the variation of parameters comes in. And remember that in order to use the variation of parameters, we need to have something to work with. We need to have a part of the solution. And in this case, we do have something to work with. We have y1, which is equal to c1 e to the r1x. So now what we do is we vary the constant, we vary the parameter. we vary the c1 over here. So let's test it out. We have y is equal to c, which is now a function, c of x times e to the r1x. So I've written down the expressions for y prime and y prime prime, and you can differentiate our trial solution to verify these expressions. So now I've plugged in our trial solution into our differential equation, which gives us this messy expression, but we can simplify it. Indeed, we can factorize by e to the r1x and divide by e to the r1x. And the reason we can do that is because we know that the exponential always spits out a positive non-zero value. So now we get this relatively neater expression. And what we do is we group the c's together. So we group these three terms over here, and we also group the c primes together and the c prime prime. Doing so, we now have this really nice equation. And why is that? Well, because we know that R1 is a root to our polynomial. So this, which corresponds to the polynomial, is actually equal to 0. And similarly, we know that R1 is equal to R2, and the discriminant is equal to 0. And what does it mean for the discriminant to be equal to 0? Well, it means that R1 can be written as the middle coefficient, A1. So actually negative A1 over 2 times, well, the coefficient over here, so A2. So negative A1 over 2A2. And so if we plug in our expression of R1 into this expression over here, we get 0. And therefore this means that A2 C prime prime is equal to 0. One important point I want to emphasize before you move forward is that the whole idea behind the variation of parameters method is that we have one part of the general solution, y is equal to c e to the r1x. And what we do is we vary the constant, so we turn it into a function. And so now we have a new trial solution, and we see the conditions that this function over here, c of x, has to satisfy in order for our new trial solution to be a solution to the differential equation. And what we have done here is that we have shown that in order for y to be a solution to this differential equation, a2c prime prime has to be equal to 0. So this is the condition that our new function, our varied constant, has to satisfy. So now we need to solve this differential equation, which is the same as c prime prime is equal to 0. And what we do is we integrate twice to get that c of x is equal to c1 of x plus c2, where c1 and c2 are integration constants. And plugging in our expression of c of x back into our solution y, our trial solution, we get that y is equal to c1x plus c2 multiplied by e to the r1x. So this is the general solution to this second order homogeneous differential equation. And the reason why it's a general solution is because we have two integration constants. And there we have it. We have derived the solution, well, the set of solutions to our homogeneous second order differential equation. We need